I'm going to work a couple of Dalton's Law problems for you because I think Thursday in class I may well have confused many of you more than I helped with the first Dalton's Law problem in the worksheet that we worked on. So before I work a problem, I just want to sort out, there are two basic types of Dalton Law problems. And the first is just real simple. You use Dalton's Law anytime you have a mixture of gases, and it allows you to, as long as you know the individual pressures of each gas, and those are called partial pressures, you can add them up and that will give you the total pressure of a mixture. That's quite simple. You may have a little bit of hiccup using this equation, which allows you to directly calculate the partial pressure of a gas if you know its mole fraction. Okay, so you may remember from Thursday in class that mole fraction is just the moles of whatever gas you're interested in divided by total moles of gas. And if you have that fraction and the total pressure of the mixture, you can calculate any individual partial pressure. And that's basically because in gas form, moles are directly proportional to pressure. Okay, so the problem that I stumbled on in class and ended up confusing several of you on is a multi-step problem. It's a Dalton's Law problem, and is virtually always the type of problem that says we have collected some gas over water, and it asks you to correct for the presence of water vapor pressure. If you collect a gas over water, it does pick up some gas form of the water vapor, and in order to get the partial pressure of the dry gas by itself, you have got to correct for the pressure of water vapor using Dalton's Law. And so that's pretty easy, I think. You just look on that table of water vapor pressures at a particular temperature and then solve for the pressure of the dry gas. Where I goofed up in class and where I want to kind of focus on in this little lecture is the second step of that problem. Typically is the question asks you to find or calculate other properties about that dry gas. They may ask you for the pressure. Well, no, you just solve for pressure. Never mind. They may ask you for the volume or the number of moles, or they may give you a whole different set of conditions than the conditions that the dry gas was collected at, and ask you to determine properties under these different conditions. So the bottom line is, if you collect a gas over water, it's likely going to be a two-step problem. Okay, the first step, correcting for the dry gas, and the second step, using either the ideal gas law or the combined gas law to calculate some other property. So now I'm going to work through the first problem on the Dalton Law of Partial Pressure worksheet, which is in the Contents section, Chapter 5, in class worksheets. That question said, the volume of hydrogen gas collected over water. So as soon as you see that phrase, collected over water, that should prompt you to write this format of Dalton's Law. Okay. And so I'm not going to worry about the second part of the problem. That's just kind of how I approach it. I'm going to solve this first part first. And so you will always get the partial pressure of water vapor at a particular temperature. It'll either be given to you or you find it in a table of water vapor pressures. The only thing you need to know is the temperature. So we need to know the partial pressure of water vapor at 18 degrees Celsius. In case you haven't noticed yet, in the Chapter 5 in-class worksheet section, there also is an entree called vapor pressures of water to use with Dalton law calculations. Anyway, that if you click on that, it'll pull up a table of water vapor pressures. So this table says that at 18 degrees Celsius, the vapor pressure of water is 15.5 torr. Okay. Make sure all the units of pressure you have match one another. All right, so we are solving for the pressure of the dry gas. And in this case, the total pressure, if you're collecting a gas over water, you're doing it in an open container, so it's at atmospheric pressure. So this P total, pressure total, is whatever atmospheric pressure is, and they gave that to you as 780. Now they're using millimeters of mercury. This table for water vapor was in torr. If you didn't realize this already, torr and millimeters of mercury are identical. So 780 millimeters of mercury actually equals 780 torr. Rearrange this equation to solve for the partial pressure of dry gas, and it is then 780 minus 15.5, and that equals 764.5 torr. So now we'll worry about the second part of the problem, but just even being able to do that will probably get you half credit. Before I open a new page, let's analyze what the rest of the question is asking. It says, what is its volume dry at STP? If they asked you for the volume of this dry gas under the existing conditions, okay, so if it was existing conditions, you would use the ideal, can't spell, the ideal gas law, PV equals nRT. I think I need to break down and open a new sheet. But what I missed in class is all of the conditions that were changing. So you need to not be like me and take a moment and analyze and see whether temperature, pressure, and or volume have changed. Okay, so what does STP mean? So now we're going to go to the next page and set out how we work the second part of the question. Okay, so the new conditions for that gas are STP. So that means that they want us to calculate conditions for that gas at a temperature of 0 degrees, which is 273 Kelvin, and an atmospheric pressure of 1 atmosphere, or 760 torr, depending on what units we need. Now, since the gas, when it was collected over water, was collected under different conditions than STP conditions, anytime conditions change in a gas, you need to use the combined gas law. So I'm just going to go ahead and write that. Now, if one of these variables doesn't change, if it remains constant, you can scribble out that variable and you'll end up with Boyle's law or Charles' law or Gay-Lussac law. But even if you don't scribble out, it won't hurt. If you plug in the same value, let's say for temperature, and it doesn't change, you're still going to get the right answer. So here's the combined gas law. So let's let the one values be the original conditions that the gas was collected under. At this point, I want to emphasize that the answer key for problem 1 is wrong. So the answer key for problem 2, however, which is very similar, is correct. But in trying to get ready for this, not only did I confuse you, the answer key confused you. And so let's discuss what these initial values should be. The original pressure of the entire mixture was 780 torr. However, we are trying to find, the question asks us for the pressure of just the dry hydrogen. So P1 is going to be the pressure that we just found for dry hydrogen. The answer key has the total atmospheric pressure. So P1 is 764.5 millimeters of mercury, or torr. The volume, now we're going to assume that the volume of the wet gas is very similar, identical to the volume of the dry gas. And so V1 is 453 milliliters. And T1 was at 18 degrees Celsius, so we need to convert that to Kelvin. All right, so the new conditions are STP, and they want to know the volume of the dry gas under STP conditions. So second pressure would be, 760. We're solving for the second volume. And second temperature is, standard condition is 273 Kelvin. All right, so now all we need to do is solve for this. The left-hand side of that equation comes up to 1190, and now we have that equal to 760 divided by 273, all times the second volume. And so 760 divided by 273 is 2.78. And so that means the second volume is simply 1190 divided by 2.78, and that equals 427 milliliters. That is the new volume of the dry gas under standard conditions. The original volume, if you remember, it was 453 milliliters. It's reduced, or the volume's gone down quite a bit, which makes sense because our temperature has gone from 18 degrees Celsius down to 0 degrees Celsius, which makes volume shrink. So that's it for problem 1. I would, if I were you, work problem 2 in that same worksheet. The answer key is correct for that one. And that's it for this video.